Hello everybody, today we'll talk about multispectrum graphs. So when you perform sound recordings, you're actually capturing data in the time domain. So if you look at this time signal, the y-axis represents the pressure fluctuations and the x-axis is the time axis. But in order to make sense of the signal, in order to understand what is the signal composed of, it's important to look at the frequency domain. It's important to understand what frequencies are present in the signal that are making the signal. So in order to do that, we need to perform the fast Fourier transform. First, let's listen to the signal. Alright, so you listened in the time domain, but now it's important to look at it in the frequency domain to understand what is it made up of. So we perform a fast Fourier transform and we here get the line spectrum. So the y-axis is the sound pressure level in decibel, whereas the x-axis is no longer time axis, but rather frequency axis. So now we know what is the signal made up of. But there are lots of frequency lines here. It'd be better if we can see it, if we get a broad overview, like, for example, we can look at in the octave band spectrum like this. So now we get a clear broad overview of what frequency bands are actually present and making the signal. So we can understand that the 500 hertz band is the most dominant, followed by 2000 and 1000 and so on. But it's good that it gives us a broad overview. It'll be really nice to know what are the frequencies in that band that are responsible. For example, this is the 500 hertz band. This is the center frequency of this band. Now, this band has a lower limit frequency and an upper limit frequency. And this is the range of this band. Now, any frequency in this band is going to contribute to this band. So what I'm trying to say here is that this 500 hertz band doesn't mean that 500 hertz frequency is the most dominant. It can be the case, it cannot be the case as well. There can be any frequency in this band that can be the most dominant and still contribute to this band. If you want to learn more about octave bands in detail, you can check the link in the description below. So it'll be really nice to see the both information together. For example, both the octave spectrum and the line spectrum together so that we can get best of both worlds together. So this is a multispectrum graph where we're seeing both the octave bands and the line spectrum together in a single graph. So the y-axis represents the sound pressure level in decibel scale, but now there are two x-axes. So the lower x-axis represents the octave band frequencies, the 1x1 octave band frequencies, and the upper x-axis represents the line spectrum. Both are frequencies, but then we're viewing it in different scales. And here the most important thing is that, as you can see here, this was the 500 hertz band was the most dominant. As it turns out from the line spectra, the 500 hertz frequency is not actually contributing to that band. Those are the other frequencies that are actually contributing to that 500 hertz band. So it's really important to look at this graph, because if you simply look at the octave 1x1 spectrum, what conclusion you can draw is that, okay, the 500 hertz band is the most dominant. But then it's important, it can be the case, but it cannot be the case as well. In this case, it's not the case. It's not that 500 hertz is actually contributing to that band, but other frequencies are contributing to that band. So that's the advantage of it. So if you look at 1x1 octave spectrum, you get information. You get a broad overview, but you don't know which exact frequency is responsible. But if you view in both octave and line spectrum, you get best of both worlds. You know which band is responsible as well as which tonal frequency is responsible. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.